In this lecture, we will discuss about how to find out stiffness factors for beams with different end conditions. First, consider the beam with hinged at both ends. So now we apply some moment M at A, support A. Because of this applied medium, the beam will bend. That means we will have some rotation beta at support A. Okay, that we call as delta AB. In support B also will some slope, but we are focusing only at support A. So therefore this is the bending moment diagram, because there is no other external span on the span, external load on the span. Okay. So by applying slope deflection method, since there is no span load, the fixed end moments are 0. That is, moment M FAB is equal to M FBA is equal to 0. Now we can straight away apply the slope deflection equation. Okay, that is MAB is equal to 2EI divided by L into 2 times theta A plus delta B plus 0, because there is no relative displacement. So 0 plus 0, because there is no fixed end moment. This we can consider as expression 1. Similarly, we can compute MBA, which is equal to 2EI by L the whole into theta A plus 2 times theta B. Other parameters are 0. So this is expression number 2. And we know that the support B is hinged and there is no external moment applied. So sigma MB is equal to 0. From this we get, from expression 2, we get delta B is equal to minus of delta A. So this value, if you substitute in expression 1, we get the value of MAB in terms of theta A. Therefore, 3EI by L into theta A. And we know that already, that is, moment is equal to K times theta. That is, moment is equal to, or the applied moment M is equal to stiffness times the rotation caused by that moment. Here the rotation MAB is the moment at support A. The delta A is the rotation caused by that moment MAB. Therefore, the remaining parameters, that is 3EI by L, should represent as a whole the stiffness of the beam. Therefore, this is equal to K times theta A. Therefore, stiffness of the beam K is equal to 3EI over L. So this is the stiffness of the beam when the far end is hinged. So the next case is the beam hinged at one end and fixed at other end. So here also we follow the same procedure as that of the first case. Since the far end is fixed, whenever we apply some moment at one end or the hinged end, so some portion of the moment will be induced in the far end, which is fixed. So now we call the applied moment as M, and the induced moment at the fixed end is M dash. So support A is hinged, where we apply moment M, and the far end B is fixed, in which M dash moment is induced. And see the direction, okay, this is the direction of the applied moment, the same direction, okay, M dash also. Now there is no span load, therefore fixed end moment is 0 at each support. That is MFAB is equal to 0, MFBA is equal to 0. And also we will have some rotation at A because the support is hinged, but the support B is fixed, therefore there is no rotation at B. That means we will have theta A, but theta B is equal to 0. So now applying slope deflection method, we will get M AB is equal to, which should be equal to M because we apply moment M, 2 EI by L into 2 theta A plus 0 other parameters, that is theta B is 0, delta is 0, fixed end moment is 0. Therefore 4 EI by L into theta A. Okay. So next M BA, which we assume as M dash, is equal to 2 EI by L into theta A. Which is equal to 2 EI by L into theta A. But actually this value is equal to M by 2. That is M dash is equal to M by 2. So here we get M is equal to some times into theta A. This sometimes which is equal to the stiffness K, because we know M is equal to K theta, therefore this is K theta. Okay. So therefore the conclusion is the stiffness of the beam when the far end is fixed is equal to 4 EI by L. This is the stiffness factor. Okay. Similarly here we get M by 2, that is M dash is the induced or carryover moment at the support, at the fixed support. So half of the moment will be carried out to the far end if the far end is fixed or the interior supports. Okay. So the moment required to rotate the near end through unit angle, that is theta A, theta is equal to 1. Without translation, when the far end is fixed, is 4 EI by L. Now we will see the next case. If we have more members at a joint, what would be the stiffness factors? So this is the scenario. Here we have fixed support A, fixed support C, this is a hinge support B, this is also hinge support D, and the meeting point is O. At O we apply some moment M. So this M will be resisted by, or the moment this M will be distributed to all the 4 beams. Okay. So based on the stiffness of each member, and all the beam will be subjected to the same rotation, beta. Okay. So rotation of the joint is beta because the joint is considered fixed, or okay, due to fixity, the joint will experience the same rotation. But the same rotation is not guaranteed at the supports. Okay, at the ends. Only at a joint we will have same rotation. So for equilibrium, this M, applied M, should be equal to the summation of the moment of resistance or moment resisted by each member. That is, M is equal to MOA plus MOB plus MOC plus MOD. But we know how to represent moment in terms of its stiffness and the rotation. That is, M is equal to K theta. That is, MOA is equal to KOA into theta. Okay. So which we assume K1 theta. So it's equal to 4 EI by L into theta. Okay. Why 4 EI by L? Because this is OA, KOA, and OA, this support is fixed, that is, far end is fixed, the applied end is O, far end is fixed. If the far end is fixed, then the beam will have this stiffness, that is 4 EI by L. That's why K1 or KOA is equal to 4 EI by L into theta. Similarly, for other member, we will get, that is, MOB is equal to KOB into theta is equal to K2 theta is equal to, this is hinge support, therefore 3 EI by L into theta. So if far ends are fixed, then we will have 4 EI by L. If the far ends are hinged, then we will have 3 EI by L. And now we substitute these values in this equation. Okay. Or MOA divided by KOA is equal to theta. Similarly for others, MOB divided by KOB is equal to theta. So theta is same for all. Therefore, MOAB divided by KOA is equal to MOB divided by KOAB. Okay, and so on. Therefore, we can represent as M1, that is MOA, is to M2 is to M3 is to M4 is equal to K1 is K2 is to K3 is to K4 ratio. Okay, because M1 divided by K1 is equal to theta. Theta is same for all cases. Or M is equal to is K1 plus K2 plus K3 plus K4 theta. That is absolutely those values. So which is equal to sigma K, summation of all the stiffness of the jet joint into theta. Okay. Therefore, theta is equal to M divided by sigma K. And we know that M1 is equal to K1 theta. Therefore, K1 into theta is nothing but sigma divided by M divided by sigma K therefore M1 is equal to K1 divided by sigma K into M. So here this M is the moment applied at the joint, but M1 is the moment distributed to the beam OA. How much amount is distributed? This much amount of, okay, this is the percentage or distribution factor. This is the whole moment. So this is the fraction, some fraction of this moment, the whole moment that will be distributed to OA. Therefore, this is the distribution factor. So distribution factor is K1 divided by sigma K. Okay. So the conclusion is the moment which tends to rotate a joint without translation will be divided amongst the connecting members at the joint in proportion to their stiffnesses. So in the next video, we will discuss about some more technical terms like distribution factor, rotational stiffness of joint, relative stiffness, carryover moment, carryover factor, etc.